Welcome to Boson Buzz, where we dive into the coolest scientific ideas and breakthroughs shaping tomorrow's world. For centuries, we have looked up at the night sky as a symbol of pristine emptiness, an infinite black canvas dotted with points of light. But the reality of Earth's orbit today tells a different story. It has become a cluttered celestial junkyard, a shell of technological debris surrounding our planet. This graveyard is filled with the ghosts of our spacefaring ambition. Thousands of dead satellites zip around at unimaginable speeds, spent rocket stages tumble endlessly, and countless fragments from past collisions and explosions form a swirling cloud of shrapnel. This isn't just an aesthetic problem, it's a deadly and escalating hazard. A single paint chip, traveling at orbital velocity of over 17,000 miles per hour, can deliver the kinetic energy of a bullet. This growing shell of space junk now threatens functioning satellites that power our GPS, weather forecasting, and global communications. It endangers the International Space Station and could one day trigger a catastrophic chain reaction of collisions known as the Kessler syndrome, potentially trapping us on Earth by making vital orbits too dangerous to use. We have a mess to clean up and the ultimate high ground, and the cost of ignoring it is the future of space exploration itself. But what if we could fundamentally change our perspective on this problem, turning a catastrophic threat into a golden opportunity? What if this dangerous debris isn't just a liability, but an untapped, floating mine of raw materials that we have already painstakingly and expensively launched into space? This is the core revolutionary idea behind the concept of the Orbital Recycling Center, a vision that completely reframes our approach to space infrastructure. Instead of seeing a dead satellite as worthless, hazardous junk, we can learn to see it as a pre-processed resource, containing high-grade aluminum, titanium, sophisticated alloys, and even valuable electronics like circuit boards and solar panels. Launching these materials from Earth is astronomically expensive, a brutal physics problem that costs tens of thousands of dollars per kilogram to break free of our planet's gravity, which severely limits the scale and ambition of what we can build in space. By learning to harvest, process, and repurpose what we've already left in orbit, we can break this costly and restrictive cycle, creating a closed-loop system in space. The visionary goal is to stop simply adding to the junk pile and to start actively mining it, transforming our greatest orbital liability into our most valuable extraterrestrial asset. This is the essential first step toward a sustainable, permanent human presence in space, where we stop being visitors and start being residents who live off the land, or in this case, off the orbital environment we have already created. Achieving this ambitious vision requires the development of two key, interconnected technologies. The first is the cosmic tow truck, or a service spacecraft. These are not traditional satellites. They are agile, intelligent, and highly autonomous robots designed to safely rendezvous with a piece of space junk. Using advanced sensors, robotic arms, nets, or even harpoons, they can capture a defunct satellite or a large piece of debris. Once secured, they have a choice. They can push the object down to burn up in the atmosphere, or, more importantly, they can tow it to a central processing station. This station is the second key technology, the orbital factory. Imagine a facility equipped not with smelting furnaces, but with advanced 3D printers that use metal as their ink. These printers would use the shredded and refined metal from the old satellites as their raw material, fed by robotic arms that deconstruct the captured junk. They could then print brand new parts like structural beams, satellite components, or even entire new structures, all without a single new launch from Earth. The process of orbital recycling begins with the complex, slow, and delicate dance of capture, a high-stakes orbital ballet. Before a recycling tug can even cautiously approach a derelict satellite, it must first spend days or weeks carefully assessing the target from a safe distance. Many of these objects are tumbling erratically, spinning end over end in a chaotic and unpredictable manner, making them incredibly dangerous to get near. The service spacecraft must first match this dangerous tumble, a breathtaking feat of precise autonomous navigation and control, before it can even attempt to secure the object with a specialized robotic grip or a net. Once successfully captured and stabilized, the real, meticulous work begins. The satellite is then slowly and carefully moved to a safe, designated processing orbit, a celestial junkyard far away from the valuable traffic of active spacecraft. Here, a suite of advanced robotic systems begins the intricate work of disassembly, a process that must be largely autonomous due to communication delays with Earth. These robots would carefully cut, unscrew, and separate different materials, sorting valuable metals from toxic fuel residues, outdated electronics, and other composite materials. This detailed sorting is absolutely crucial. It ensures that the purest, highest quality materials are fed into the subsequent manufacturing process, which is essential for creating reliable and high-strength new components. This entire phase transforms a chaotic, tumbling piece of dangerous junk into an organized, valuable inventory of space-based raw materials, meticulously cataloged and ready for its second life as part of a new station, satellite, or deep space vehicle. With a steady supply of raw materials, the orbital factory can begin its transformative work. The most promising technology for this is additive manufacturing, or 3D printing in zero gravity. In the vacuum of space, without the interference of gravity, it is possible to create structures and objects that would be impossible to form on Earth. This, in space manufacturing, could produce massive, lightweight girders for new space stations, custom-designed parts for repairing other satellites, or specialized tools for astronauts. The products wouldn't be limited to simple beams. They could include complex integrated components, potentially even printing new satellites designed specifically for assembly in space. This capability would fundamentally change the design philosophy for space missions, freeing engineers from the constraints of rocket fairings and launch forces, and allowing us to build structures that are larger, more delicate, and far more ambitious than anything we can currently launch. Of course, establishing a functioning, profitable industrial economy in the harsh, airless, and high-radiation environment of space is a monumental challenge that extends far beyond the pure engineering. The technology for automated, precise capture and disassembly of uncooperative, tumbling objects is still very much in its infancy, requiring leaps in robotic autonomy and machine vision. The 3D printing and manufacturing processes must be perfectly reliable and largely self-repairing, as a critical failure in orbit could be millions of dollars away and impossible for humans to repair quickly. There are also profound, unresolved legal and diplomatic questions that must be addressed on a global scale. Who owns the property rights to a defunct satellite? If a company from one nation captures a satellite launched by another, who has jurisdiction? Can a private corporation claim legal ownership of an object they have salvaged from a graveyard orbit? How do we, as a global community, regulate this new industry to prevent conflict, ensure safety, and guarantee that the benefits of this new space-based economy are shared for the benefit of all humanity, rather than a select few? Furthermore, the initial multi-billion-dollar investment required to launch the first fleet of recycling tubs and processing facilities is enormous, requiring a long-term vision and collaboration between governments and private industry that must transcend short-term political and economic cycles. The path forward is as much about building unprecedented international cooperation and creating entirely new legal frameworks for space as it is about the breathtaking feats of engineering required to make it physically possible. The Orbital Recycling Center is more than just a clever solution to space junk. It is the foundational industry for a sustained and growing human presence in the solar system. It represents a fundamental shift from a disposable, throwaway model in space to a circular, sustainable economy. By learning to live off the land, or in this case, off the orbital environment, we can construct massive space stations, fuel depots for missions to the Moon and Mars, and vast solar power arrays to beam clean energy back to Earth. This circular economy in space would make these ambitious projects financially and logistically feasible for the first time. It transforms space from a destination we merely visit into an environment where we can truly live, work, and build a future, using the materials we once thought of as trash. We are on the cusp of a new era, moving from an age of cosmic consumption to one of cosmic conservation, ensuring that the final frontier remains open for generations to come. If you found this as fascinating as I did, do me a huge favor and hit that like button. Share this video with anyone who loves science or just cool, futuristic tech. And of course, if you want to stay updated on this and other amazing breakthroughs, make sure you subscribe to the channel. Thanks for watching, and I'll see you in the next one.